Now we're going to look at differentiation using logs. So first we'll have a quick look at the log function. So the log function is like the inverse of exponentiation. So if you have a to the power of b equals c, that's the same thing as saying that the log of c to the base a is b. So the log is the power to which you have to raise the base in order to get the number. So you raise the base a to the power b to get c. There are a couple of special bases that we're interested in. One is the base 10, and if something is log to the base 10, we just write that as log on its own. When we want to write the log to the base e, that's the number e, we just write that as ln, stands for natural log. Here is a list of laws for exponents and corresponding laws for logs. So if you multiply two numbers with different powers, you add the powers. The corresponding log rule is that the log of xy to the base b is the log of x to the base b plus the log of y to the base b. And the same for dividing and subtraction. So if you have log of x over y, that's log x minus log y. And for powers, if you have the log of x to the power of n, that's just n times the log of x. And the log of b to the base b is always 1, and the log of 1 to any base is always 0. So here's an example of where we would use logs to make differentiation easier. So if you look at this thing, y equals all that, we could use the product rule or the quotient rule a few times along with the chain rule and calculate all this out. But it would take forever. Instead, what we'll do is we'll take the log of both sides, we'll use the laws of logs to simplify the right hand side, then we'll differentiate both sides implicitly in the case of the left hand side, and then we'll be able to solve the equation we have left to get dy dx. So first we take the log of both sides. Now we can use the laws of logs to simplify that right hand side. So that top half is the log of 2x minus 3 plus the log of 4 plus 3x all squared. X squared all squared. Then the terms on the bottom in the log are taken away. So it's minus the log of 4x minus 3 minus the log of 5 minus 4x to the power of 3. Then we use the another law of logs. So we say that these powers actually come out in front. So that's the log of 4 plus 3x squared to be squared before the log is applied. That's important actually. So those powers come down in front of the logs. So now we have this expression and we differentiate both sides of it with respect to x. And we get the first term, log of y becomes 1 over y dy dx by implicit differentiation. Then the log of 2x minus 3 by the chain rule. The derivative of log x would be 1 over x. So the derivative of log of 2x minus 3 is 1 over 2x minus 3 times the derivative of what's in those brackets, which is just 2. Same for all of these terms. So the log of 4 plus 3x becomes 3 times 1 over 4 plus 3x, and that 2 is still in front. And the same for the last two terms. So then we just sort that out. And finally, we can multiply both sides by y to get dy dx equals y times all of that. Now in this case, we do actually know what y is as a function of x. So as a last step, you could substitute back in y as a function of x and get dy dx explicitly as a function of x at the end. I'm not going to do it here. I'm not going to ask you to do it in tests and stuff, just because we know that y is explicitly a function of x, so we don't need to write it down. So there's your final answer.